Right, recording is rolling. So this is Wednesday. There's like hours of information I want to get to you guys. Well, got to pick some stuff just for a 45-minute class. So tell you guys a bit about these formulas. There's more stuff I want to tell you guys, but I'm going to postpone that to another day. Maybe give you guys a little bit of information here and there as we go along. Build your knowledge organically, and I really want to focus on a lot on free body diagrams today. So there's a PowerPoint that I'm going to be referring to that has been posted to Google Classroom. So the PowerPoint slides you guys see are on Google Classroom, as are all your guys' new posters that are hanging from the ceiling here. I did post those also, so those are there. Okay. Let me start with this top one. You guys know this is Newton's second law of motion, right? F equals ma, force equals mass times acceleration. Okay. Except the way I told you guys, I actually prefer, I think a better way to think of it is written in fraction form. Acceleration is caused by force acting on a mass. Okay? But really, it's, say, what if you had like 5 different forces on an object? Or like, remember the guys like pulling a donkey? There are like multiple forces on the donkey, or all the monkeys pulling on the bananas. So it's really the net force is what we're talking about, right? Once you figure out what is the net force that results from all this force, whether you tip to tail vector addition or component analysis, there's some net force that results because any object can only accelerate in one direction with one magnitude like that. Now, here's Newton's second law of motion then. And you can see that force and acceleration are directly proportional. So if you double the force, you double the acceleration, triple the force, triple the acceleration. But acceleration is also inversely proportional to the mass. So the more massive, the less it's going to accelerate. Guess that? Here, I'll give you guys an example right here. Let's say I got this little 10-gram mass right here. I got 1,000 grams, 1 kilogram. I'm going to put the same force on both of these guys. Okay, watch this. Oh, man, how far did that go? Not very far. How about this guy? So, same force on both of these guys. Pew, pew, pew. This guy hardly wants to accelerate at all. Huge mass. This guy, fly across the accelerated so much because it has very small mass. Inverse relationship going on there. Now, you can modify this to get a slightly different story. What if the only force, and therefore the net force of an object, is its own weight? Right? It's gravity pull from Earth. So I could say weight as one type of force, modifying this a little bit. Right? So it's under the influence of only one force, its own weight. Say you toss this off a cliff, and it has some mass. And if you divide that out, you get a very special kind of acceleration called what? Yeah, gravity, like free fall gravity. And you guys saw Paul Hewitt take you guys through this story yesterday. Remember the 2 kids on the island chasing the Hershey bar, trying to figure out, hey, which of these is going to hit the ground first if you drop them at the same time? Now you guys know the answer to that story. The answer is they hit the ground at the same time. But why do they accelerate towards the ground at the same rate? Well, from this point of view, you see, remember the first kid was thinking, well, if something weighs more, has more force, that should speed up its acceleration, it should have greater acceleration, which in isolation actually would make sense, right? The second kid said, well, hold on, the bigger object has more mass, and more mass means more inertia, so that should accelerate less, which again, in isolation is true. But those two stories together, you put it together, and those two effects cancel each other out, so all objects fall at the same rate at the surface of some planet. And on Earth, that rate is about 10 meters per second squared. It's like 9.8 meters per second squared. Now, you can take this so you can rearrange it. Watch what happens here. If I do weight is equal to, and I cross multiply with the m, wouldn't that be m times g? Yes, is there? Okay. In this class, I'm going to label a bunch of vectors mg. Every time I do that, I'm referring to the weight. Notice mg in a different context, it might mean something else. If you guys are like taking medication or something, then as a unit, this might mean milligrams. That's not the context in physics. In physics, this is 2 variables multiplied together, mass times the free fall gravity on the planet. Now, AP will accept that for weight. AP also accepts F sub g. You'll see both of these on AP exams. Just in my notes as I write things, I prefer mg because I've just done it that way since forever. Okay. Something else I want to mention about Newton's second law of motion is I want to go back and look at the units associated with this. Let me put it back in its non-fraction form. F equals ma. Can't see that here. Same thing as this. This and this are the same thing, right? Put in that force. Now, you guys know that mass is measured in kilograms. And remember, this is the only base unit that has a prefix baked into it. Right? So 1 kilogram is 1,000 grams. Right? but it's just, this is the base unit of mass in this class. It's this guy right here, 1 kilogram. And you guys know what acceleration is. It's a rate change of velocity, which is meters per second per passing second. That's also called meters per second squared. You guys know that? And also, you guys know what force is. Force is measured in newtons. And if for no other reason, you know that because you guys have gotten your hands on these spring scales. And when you put some force on a spring scale, it's measured in some number of newtons. Right there, there's 5 newtons of pulling force. There's 8 newtons of pulling force, 10 newtons of pulling force to stretch that spring. Right? You see that? So different numbers. And the force is just a push or a pull. So, hey, look at these units. Now you guys know that 1 Newton, which is just a way to quantify a push or a pull, it's a force, is actually a composite unit, and it breaks down into some number of kilograms meter per second squared. So whenever you push on something, pull on something, if you have some weight, that you can quantify that in terms of this composite unit. It actually breaks down like this, kilogram meter per second squared. Now, the first day you walked in this class, if you saw something like that, think, okay, that's a crazy jumble of units. But now you see the context for this. This definitely makes sense. Because if you push on some mass, it causes it to accelerate. This makes sense according to Newton's second law of motion. Now, I told you guys we're going to focus largely on free body diagrams today. So give you guys some notes about free body diagrams and then go into friction just because there's going to be some friction forces on some of my examples. So free body diagram, commonly abbreviated FBD, free body diagram. You guys are going to see these all over the place in this class. These are a real big deal. It's just a diagram showing all force vectors. I have some other stipulations too that were on the PowerPoint when you guys walked in, but here's the really important takeaway, is that it's force vectors and only force vectors. Now, you guys have seen many kinds of vectors in this class, like displacement vectors, velocity vectors, acceleration vectors. Those are not force vectors. On the free body diagrams, you only care about the force vectors. So if something's in motion, moving in some direction at some speed, is the speed of the object represented in a free body diagram? No, only forces. So let's look at an example. So say, for example, let's say you got a block and you're pulling a block across a surface. Now, let's say you're pulling it at constant speed. Or maybe even better, I'll say constant velocity. Constant speed and constant direction, right? Constant velocity, something like that. I wonder what the free body diagram would look like for a scenario like that. Okay? So let's draw this out. I'll draw the floor just for visual context, although strictly you don't need that for the diagram, but I'll just put it there. You got a block. There's a block on a surface. Draw center mass dot right there, like that. Okay. How about you guys are attention to draw that? I'll actually demonstrate this in front of you guys. So here's my block. Here's what I'm using to pull it with, and since it's a spring scale, I can even measure in newtons what the pulling force is. Okay. So pull this across, okay. And then just like that. So what's the free body diagram for that situation right here? That situation. Okay. Well, let's think about all the forces on this block at the moment. I bet this block has a weight. It has a weight. So draw a force vector straight down, and I'm going to label that mg. You could also do f sub g if you want, but I'll do mg. Okay. That's the Earth pulling that block down. Okay. Now, if that's the only force vector you do and you walked away, then what you would be communicating to whoever's reading this free body diagram is that that block is in free fall, like you tossed it off a cliff, and it would actually be accelerating straight down, wouldn't it? Okay. But that's definitely not what's going on. The table is holding it up. The table's holding it up with the force I'm going to call F sub n. Okay. Notice I made it the same magnitude. You see those two arrows are the same length? Is that? Okay. Because the table's holding it in equilibrium in the vertical direction. F sub n stands for what's called the normal force. Normal force. Okay. Do you guys remember maybe from a math class? I don't know. What the word normal means? Like if two lines are normal to each other, that means they're what? Perpendicular. Perpendicular. Okay. So perpendicular. Well, perpendicular, but perpendicular to the surface. If anything is ever like resting on the surface and there's some kind of support force, which is what this is, it's a support force from the table. That support force is always perpendicular to that surface, which if it's just a horizontal table, just very straightforward, it's just straight up, exactly like from there. Okay? But where this is going to become more involved, getting kind of into the weeds, but this is sort of a flash forward. Right? So we're working our way up to this. Okay? Remember a block on an incline? You guys go, hey, look, that's the weight, mg, that's the weight straight down. You guys know how to break that weight into components. I made a whole deal about introducing a Cartesian system that's aligned to the surface. Why is that? Well, because we're going to add more to the story. Look at this support force right here, F sub n, the normal force. You guys see that? This is a support force from the surface. Now, is this support force exactly vertical against gravity? No, it isn't. It's perpendicular to the surface. It's even named that. It's called the perpendicular force, the normal force. Could you guys imagine? It's good to be able to play around with variables in your head. If you took this angle theta all the way to 0, this normal force actually would be straight up, but only in that case. What if you ramp this angle up the other way to like 80 degrees from the horizontal, right? Or even more extreme, make it a vertical wall. Wouldn't the normal force in that case just go to 0? Put the block on just let it go. There's no support force that way. Right? And then 80 degrees might be a very tiny force. So hey, I bet it gets the normal force getting less and less the more you ramp up that angle. Is that? So it's some component of the weight. So we'll come back to that. I want to build up to that, but just to show you guys that. All right, so right now we've got this similar situation. And see, I did say you're pulling block across. Now pull, that means there's some kind of force going on. So let me slap in an applied force here. I'm going to make it shorter than the first two vectors, and there's a reason for that. I'll call it maybe F applied, like an applied force. An example I showed you, it was actually a spring force. Right? There was a spring force pulling this across the surface, something like that. Like that. And one more thing, though. See this last stipulation I did? Constant velocity. Constant velocity. See if I just draw this free body diagram and I walk away, is this free body diagram exactly as it's shown right now? Constant velocity.
Yeah.
Is there a net force on this block? As I've drawn it, there is a net force. See how there's a net horizontal force? Okay. Hang on. If there's a net force, then is there an acceleration? And if there's an acceleration, is it constant velocity? Ooh. Okay. What that means then is that when you see constant velocity, that means that there must be no acceleration, which means that there must be 0 net force, which means all the forces must balance. So I need something else. What force do you think is balancing the applied force? Friction. Friction. Right. And here's where I'm about to give you guys some extra notes on friction, which I guess could be helpful anyway. So I've got a whole like 2-part friction lab lined up for you guys sometime in the near future. So give you guys some notes on this today. So this is a friction force. I'll call it F sub FR. Okay. Notice I made it the same magnitude as the applied force. You guys see that? Okay. Because constant velocity, because these two need to balance out for that case. Okay. Now, friction, there's a lot of stuff I want to tell you guys about that, but for now, in the margin, I'll write this note. Friction always opposes direction of motion. I know I've been making this whole deal about free body diagrams showing only force vectors, and I underlined the word force. Notice we don't really care about velocity vectors, but sometimes I'll throw a little side arrow on here, make a fat arrow to say that this is not part of the free body diagram. I'll label it V to show the direction of motion. Okay. And I know in this case that the block is moving to the right because friction is pointing to the left. That's actually the only reason you know it's going to the right. Okay. Otherwise, see if I didn't have these forces labeled and you just saw that, it'd be ambiguous. You wouldn't know even if it was moving or not, and if it was moving, which way is it moving, to the right or to the left, it would be ambiguous, wouldn't it? Okay? If you didn't know. Okay. But once you know that this is friction force, like, okay, well, it must be either moving to the right, or it could be static friction. So, like that. Speaking of which, there are actually 2 different kinds of friction. Because how would you know that this block wasn't at rest? It might be. see, let's go back to this example. Let's do a little mini experiment right here. So I've got spring scale, weight. Okay. Notice that originally, look at this. I'm putting a couple of newtons on this, and it's not even moving at all. You guys see that? Huh. So it takes a couple of newtons just to get it going. Now, once it is going, then, okay, it'll start sliding across, and I'm applying a force, constant velocity, constant friction, all that stuff, right? But it took something to get it going in the first place, didn't it? Right? Which hints at, maybe there's two kinds of friction. There's the original, like, static friction before it broke the friction between the weight and the paper. And then there's kinetic friction once it is sliding. So let me give you guys some notes on that. So let's do this. Let's do this way. I'm going to take a whole page to do this. I'm going to kind of jump around, but there's a method to my madness here. So static friction. You get static friction when the two surfaces are not yet sliding past each other. Okay. And then once they are sliding past each other, leave some space, go about halfway down the paper, because I'm going to give you guys some notes in the middle. Okay. Kinetic friction. Kinetic friction. This is when the two surfaces are sliding past each other. Well, that's not a definition, I guess, but it's a condition for each other. It's what distinguishes this from this, right? They're each a resistive force. So this is a resistive force, this is a resistive force. It opposes the motion, just like I told you guys before. Okay. But what's some equations that go with this? If we're talking about kinetic friction, actually the equation is more straightforward. It looks like this. The friction force that builds up to kinetic is exactly equal to coefficient of friction times the normal force. Okay. And since we're talking about kinetic friction specifically, I'll even include a subscript K on this Greek letter. This is Greek letter mu. It looks like a U with a tail on it. Okay. And so you can also rearrange this. Let me do that to give you guys two different contexts for this. I could say this. I could say U sub K is equal to friction force divided by normal force. That would be the same thing. Right, you guys see that? Okay. So this is what's called the coefficient of friction. Yeah, I'll say kinetic friction. Since they're sliding, right? Mu in general is just coefficient of friction. Right? If they're sliding and you know that, then you can put sub K and say that. Okay? But it's the ratio of these two forces. Okay? Now, you guys are kind of somewhat familiar with this already by doing this this sandbox type lab. You guys remember that? Remember these like 10 mini labs? And one of the things I had you guys do, and we'll do a more extensive version of this in the near future, is you lifted the block, you dragged the block across the surface, and you recorded how many newtons of force was it for each of those. You guys remember doing that? Okay. And what you should notice is that the ratios of the forces should have been pretty similar for like different lab weights. So like if you were lifting, say like a 10 Newton weight, maybe the drag force was 5 newtons. If you lifted that would have been 1/2, right? 5 to 10 is like a half. Right, that would be what this is, like 1/2, 5 over 10, 1/2. Okay. What if you lifted something that was 20 newtons and you dragged it across the surface and it was 10 newtons to drag it? You say, well, 10 Newton weight, drag force was, 20 Newton weight, 10 newtons to drag, 10 over 20 is a half. Okay. Or what if you lifted something and it was 4 newtons and it took 2 newtons to drag it? You say 2 newtons to drag over 4 Newton weight, 2 over 4. Okay, so that you should have gotten a pretty similar ratio over and over and over again. So we got. And you can rearrange it like the first way to say, okay, well, if I know what the normal force is, which again on a level surface, nothing fancy going on, which is be equivalent to the weight. Okay. If you know what the coefficient of friction is, then you can determine what the friction force would be. Okay. Now, this coefficient of friction, this is a material property. So I'll say material property between two surfaces. There are textbook values for these. Like, for example, if you dragged this weight across wax paper or across, this actual paper you see right here, or across like a carpet, I bet it would take different pulling forces to do that, wouldn't it? Okay. Because there would be different coefficients of friction. Okay, so far? Okay. Now, there's more I want to say about that, but let me go back and fill in this gap that I told you. Remember, fill in this gap? Okay. Because before you can get to the sliding friction part, this kinetic friction, you had to break the initial friction to get there to start with. Okay. Now, this equation is going to look pretty much the same. I'll say force of friction, but now it's going to be static. Okay. I've got coefficient of friction, but I'm going to put sub s for coefficient of static friction. Coefficient of static friction, right? Multiplied by the normal force. So far this line looks exactly like that line, doesn't it? Right? But I'm going to make one little change, and it's this. Actually, I want you guys to read this out before I put this last detail. Okay? Is that you guys saw to overcome the static friction? It takes a few newtons. There could actually be multiple frictions. Like if I put a half Newton force on it, I bet there's a half Newton of friction. If I bring up to 1 Newton of force, there's like 1 Newton of friction. See, isn't it just going to mirror however much I'm pulling to balance it out? Okay? So I don't want to say equals because coefficient of static friction, that's just some material property. That's some value. Okay? I want to say it builds up to that point. It can be less than or equal to. Okay? And that's exactly as you see it on, where's this page? I had this page ready to go. Here it is. You guys, this AP equation bank. It's right. It's right here near the top. Okay. So here's Newton's second law of motion. Acceleration is net force divided by mass. Right. And right beneath that, you see where it says friction force is less than or equal to coefficient of friction times the normal force. Okay. They threw absolute value bars to say the magnitude. Okay. But that's what this is showing. That's why it's inequality. Okay. But if it becomes kinetic friction, like sliding, it just very simply becomes equal to. Yeah. Good so far? All right. Let me give you guys some example numbers, and then I want to make a graph, and then we'll move on to free-body diagrams. So some example numbers. We go back to this last page of notes and break out a red pen. So, for example, I'll give you guys an example. What if the weight was 10 newtons, just like this 10 newtons weight? This 1 kilogram weighs almost 10 newtons. Well, in that case, wouldn't the normal force straight up also be 10 newtons to balance it out? Okay. So as long as you have a level surface, nothing fancy going on, these two are equivalent in magnitude. So that's all good. Okay. And let's say that it takes so many newtons to break the initial friction, maybe like 5 newtons to break the initial friction. But once I get it sliding, it takes like 3 newtons to keep it in motion, right? Something like that. Since I've got this one in motion, I'll go with the kinetic example. So this could be 3 newtons of force from the spring scale to keep it in motion as it's sliding across. But if it's constant velocity, what does the friction force also have to equal? Yeah, 3 newtons. Okay? Because that would put it in equilibrium, wouldn't it? Remember, constant velocity doesn't necessarily mean it's not moving. It might not be moving. It might be moving, but if it is moving, it could be constant velocity. That would also be a case of equilibrium. So all the forces have to balance. There's just no acceleration. There's no net force. Okay? Okay. So those example numbers I gave you, remember I told you guys just made up example. Take 5 newtons to break the initial friction, but only 3 newtons to keep it in motion, for example. Right? Notice that example number jumped down from 5 to 3. Right? So what you'll see over and over, regardless of the materials that you pick, is that the static friction between those two surfaces, in this case maybe like the black paint of the weight in this paper, is always more than the kinetic friction if you're looking at these coefficients. So let me draw a graph to tie all this together. We're going to tie this all together with the graph. Right. Let's say you're dragging a block across a surface. I say drive, maybe pull. I like that verb more. You're pulling a block across a surface. Okay? So you got your spring scale, got your weight, you're just pulling across the surface. Okay. All that's going on very simply is this right here. Just pulling across the surface. Make a graph and think about this. What if you were looking at what is the coefficient of friction? So I'll put coefficient of friction on this axis, which is mu. That's Greek letter mu. Looks like a U with a tail on it. As a function of velocity, say between the two surfaces, meters per second. So this represents, say I'll say the sliding speed between the two objects. Okay. So at a minimum, it could be 0. Now, if there's 0 sliding speed, isn't that the static case, right? So there's some coefficient of friction that's involved with the static case, and I'll put that dot right there. And that's coefficient of static friction, mu sub s. Okay. Now, once those two surfaces start sliding past each other, you get some motion going on. Turns out that it doesn't matter if the two surfaces are sliding past each other really fast or really slow. You see about the same ratio popping up over and over again. It's pretty much a horizontal line. And that horizontal line value that it drops down to, that is the coefficient of kinetic friction. Something like that. Okay. So my example numbers were maybe, remember it took like 5 newtons to move that 10 Newton weight originally, but only 3 newtons to keep it in motion. So this might be like, for example, 0.5, and this might be 0.3. These are just example numbers. Okay. But the takeaway relationship is that the coefficient of kinetic friction is less than the coefficient of static friction. Static. Okay. And they are both greater than 0. If you had 0 friction, that would be like an air hockey table. You guys have played air hockey? Like 0 friction surface. Okay, so realistically, it's always going to be more than that. It's supposed to be an S right here. S, static. Okay. And it's typically less than 1. Like my example numbers are 0.5 and 0.3. Okay. It's not impossible for it to be greater than 1, but if it was greater than 1, what that would mean is that it would actually be easier to lift an object than it would be to drag it across the table. I was asking this question here. So if you had a car with like new tires, new paved road, and it was actually somehow easier to lift the car than to push it across the road, that would be possible. That would be a coefficient of friction of like 1.1 or something like that. That's very rare. Okay. You guys good so far? Okay, so I set you guys up with some notes about friction. That's definitely gonna come back in the future. You'll have a lab about that. There's other kinds of forces I want to talk about, but the main thing I really want to get to today are these free body diagrams. So let me share my screen, share a screen too. Okay, and like this. All right, so you guys saw this when you walked in, free body diagram. Just labeling all the forces on the object, draw them proportional to number of newtons. So in my example, you guys see right there, those two arrows are drawn the same length because they're each the same number of newtons to the force vector. Always connect the tails of the vectors to the center mass dot on the object. It'll change a little bit when we get to rotational dynamics, but for now, let's do that. AP is really strict about this rule, this third point here. Always connect the tails vector to the center mass. See that black center mass dot? And I connected the tails of the vectors to those. If you draw a free body diagram where your vectors, force vectors, are like floating out somewhere in space, that you can interpret it, you can get the right answers. Either way, AP will not give you credit for your free body diagrams unless you draw them exactly like that. Right? Remember that forces are measured in newtons, and you know about other kinds of vectors, like for example, velocity vectors and a few other ones. But guys, are velocity vectors part of free body diagrams? No. Right? Only force vectors. Okay, only force vectors. Let's look at some examples. How about a block at rest on a table? Block at rest on a table. Well, you guys just saw that one. Right? So there's a weight pulling straight down. Right? Call it mg for the weight. Sometimes AP does F sub g, so be ready to feel that too. But AP does both. Right? No, if you just draw that and walk away, then what is that block doing? Yep, falling off a cliff. So there better be some support force from the table surface. If it's a flat table, I guess that's applied, then it would just be straight up. And that's called the normal force. Okay? Normal meaning perpendicular to the surface. Okay? And notice that those are same magnitude. Okay? Yeah, guess that. Okay, next one. Block at rest on a table, pushed horizontally, but not with enough force to overcome the friction between the block and the table surface. So this block is going to have a weight, it's going to have a normal force, just like before, but now we're pushing it horizontally. Right? Pushing it horizontally. Now, right there, if you stopped at that moment and walked away from the paper, does that satisfy that premise written in white text? No. And how do you know?
You still need to show the friction.
Yeah, because there's definitely some friction going on. And notice that friction exactly balances out the pushing force. Okay? So see how that block is in equilibrium? So zero net force. Okay, so that could be possibly at rest. If you were told this was static friction, then you would know for sure it was at rest. Next one. What if there's a block on a table, you're pushing it horizontally so that the block does move with constant velocity across the surface. Okay? Now notice I drew a fat green velocity vector over here. That's not technically part of the diagram, okay? But it is helpful for one reason, and I'll tell you guys that in a minute. Okay? So this block has a weight, this block has a normal force. Okay? Now there's a pushing force. Now could you possibly be pushing something that's moving in the opposite direction? Like, could a car be rolling towards you and you're pushing it away, like, don't roll me over, right? Could that happen? That can happen. So does the pushing force dictate the direction of motion? Not necessarily, right? Just from that, you don't know if that block is moving right or left. But see that term constant velocity? Constant velocity means that is that block in equilibrium? Constant velocity, doesn't that mean zero acceleration? Which means zero net force, which means the block is in equilibrium, which means that the friction force, again, must exactly balance out the pushing force. Okay? Now, here's where the direction of motion actually sort of does matter, is because friction, remember, always opposes the direction of motion, right? If two surfaces are sliding past each other. Okay? So in that case, that's the only reason that velocity might matter for free body diagrams. Okay? But take a look at that free body diagram. And compare that to, I'm going to go back to the last slide. Back. Here's the previous one where it was just sitting at rest. Doesn't that free body diagram look exactly like forward, this new free body diagram? They look identical, don't they? So if you were not told if this friction was static or kinetic, and all you had was the free body diagram and you had none of the white text, it would be ambiguous. You wouldn't know, is that block moving at constant velocity or is it not moving at all? You would have no idea. Next slide. Block on a table pushed horizontally so that there is a net force. So we got the weight down. We got the support force from the table up. That's the normal force. Now, the pushing force is, well, the most important thing is that there's net force. So I guess actually that could satisfy the premise, couldn't it? Right? That could be an air hockey type situation, right? If there's zero friction. Well, let's go ahead and, I guess, add a friction force anyway. But if you do add a friction force, which would definitely be realistic, very importantly, notice that that does not balance with the pushing force. Yes, that see how there is definitely a net force. Right? In fact, what you could know too is that this block has to be speeding up because it must be moving to the right, and there's also a net force to the right, so the acceleration is to the right. So velocity and acceleration are in the same direction. Okay? Next one, let's have a rock and free fall with no air resistance, which is one of our usual assumptions in this class. That's about to change. We're about to bring back in air drag, but let's have one last hurrah with vacuums. So what's one force on this rock? Yeah, it's weight, the gravitational force. It's weight. Okay? What's another force? Or is that a trick question? Aha, man, tricky Griffin. Yeah, there's no other force. That's it. Okay, if you just draw that, it's in perfect free fall in a vacuum. End of story. That's it. Throw something off a cliff. Every single rock that's been dropped off a cliff, thrown off a cliff once it's left your hand, or for that matter, projectile. If you fire a cannon horizontally off a cliff, that cannonball goes into like a parabolic path. Right. every single one of those scenarios has the same three-body diagram. This could be a cannonball, I guess a square cannonball. It's like one of those South Park Canadian cannonballs, like flying off a cliff horizontally. Right? You don't know the direction of motion. All you know is that there's a force pulling straight down. Right? How about this? Rock is in free fall, but now let's bring in air drag. Huh. Also I said before terminal velocity. So now we're getting to some ideas like, I wonder how this air drag thing works out. See if you guys can draw the solution before I show you guys. So you guys drew this rock has a weight that's pulling down. Okay, so that's good. Let's say it's falling straight down. So direction of motion is straight down also. Did you guys draw an air drag that's opposing that motion? Air drag is kind of like friction. It also opposes the motion. Notice that there is a net force on that rock. So is that rock right there still accelerating? Yes, it is, because there's a net force. Is it accelerating at the full rate of gravity? Yeah, not anymore. You guys are right, not anymore. So maybe the net force on it, suppose this is a 1 kilogram rock, weighs 10 newtons. Maybe there's 5 newtons of drag force. You guys see that would give you a net force of 5, right? 10 minus 5 is 5 newtons. Divided by its mass, it might only be accelerating at 5 meters per second squared. Right? Now, the fact that it's picking up more and more speed, do you think that the faster it goes, the more the drag force is also going to pick up? Yeah, that makes sense, doesn't it? Let me flip my screen back over to projection here. And I want to give you guys, fill in some details about how drag force works. Now, this is almost certainly not anything that AP is going to ask about. This is a bit beyond anything they would ask, but I'm about to give you guys a little bit more context as to how drag force works that could help you guys think about this. So, drag force, say you have a rock, has some mass, it's in free fall, it's falling straight down. So this thing could have a weight, so mg, it's falling straight down. And because it's falling through the air, it could also have a drag force. I'll call it F drag. I'll give you guys an equation that goes with this. So an equation that you could apply to this might go like this. Seen slightly different versions of this. I'm just picking one, I think the most popular version of it. Okay. Point out what each of these things mean. So this CD is called the coefficient of drag. Think of it kind of like coefficient of friction. So something to do with the materials like that. There's actually another material property around here, and that's this Greek letter rho. Looks kind of like a curly key. That's Greek letter rho. And in this context, it means the density of the surrounding fluid. Surrounding fluid. Right. For example, suppose this rock is falling through the air versus maybe there's a lake down here and falls into the lake and starts falling through the water inside the lake. Do you think the drag force would be a lot more through the water than through the air? Yeah, definitely for sure, right? What if you had a parachute? Talk about parachutes in a few minutes. If you have a parachute through the air versus maybe you're like on a speedboat and you throw a parachute in the water, isn't there like a bunch of drag force for if that parachute's in the water, right? Because water is about 1,000 times as dense as air. So all else equal, you'll have 1,000 times the drag force through water compared to air. Right? What do you guys think that A stands for? How about this? Say you jump out of a plane. I hope you guys remember to bring a parachute. You guys remember to bring a parachute? No. Oops. Sorry. So this guy remembered. Yay. You have to do more physics. Do you want a parachute that looks, say the size of a car, or do you want a parachute that's this big? Should this be your parachute?
Maybe the size of a car.
Cross-sectional area. Cross-sectional area. There you go. That's what that is. This is your cross-sectional area. Cross-sectional area. Okay. So like this rock might have a cross-sectional area that's about this size here, isn't it? Right? That could be the cross-sectional area A, something like that, right? Okay, so the larger the area, the more the drag force. That's gonna make sense, right? And finally, you guys know what V is. Yeah, stands for velocity. I'll say speed just because whatever direction it's going, the drag force is going to oppose it anyway. And now I illustrated it out so you can think about how drag force works, but I really want to hone in on the relationship between speed and drag force, okay? Because as this is falling, the drag force is going to change. Okay? You guys see that as speed increases, the drag force also picks up. Okay? But it's actually a parabolic relationship. Like if you double your speed, what happens to drag force? It doesn't double, it becomes quadrupled 4 times because that factor 2 also gets squared. See that? What if you triple your speed? What happens to drag force? 9 times. Right? You guys see that? Right? Because squared, right? 3 squared is 9. Right? What if it's 5 times the speed? 25 times the drag force. Right? Is that? Right. So as say a rock is falling through the air, that drag force is going to pick up more and more and more. Right, here's the next thing I want to do. I think Eddie was asking about this a few weeks back. What happens when you bring in drag force? Right? So let's do that. Let's make a velocity versus time graph. Velocity in meters per second versus time in seconds. Say something as throw, or I'll say drop rock, drop rock off cliff edge. Okay. So we're watching that rock fall down all the way down. Let's do 2 different velocity versus time curves. We'll do the traditional one, and then we'll bring in the air drag. So what does the traditional one look like? Just a direct relationship where the slope is free fall gravity. Okay. Now that's with no air drag. Okay. And that's been our assumption, well, up until about today. Okay. But what if you do bring in air drag? Okay. Do you think that at some point the air drag would build up so much that it would actually balance out the weight? Right? I hope that would happen for this guy. This guy hopes that's the case. Right? That the air drag builds up. And when that happens, when the air drag builds up so much that it balances the weight, is that object, in this case, this guy, would he be in equilibrium? He would be. And what does that mean? Does that mean he stops in midair? No, that means he goes down at constant speed, doesn't he? In fact, that constant speed has a name. I bet some of you guys know what it's called. Terminal velocity. Terminal velocity, right? Now, keeping all that in mind, so once these forces balance, he goes down at constant velocity. Right? Keeping all that in mind, can you guys figure out what this graph would look like if you include air drag? Right, see if you can draw it. I'm going to give you guys a shot before I show you the answer. I'm not quite turn around the room real fast. Who's going to get this? Oh, yeah. Luke got it. Oh, Eddie got it. Tiana got it. Nick got it. Oh, sorry, yeah, Ryan got it. Deegan got it. Riley got it. John got it.
What?
I've got a bunch of winners over here. Yeah, Adam got it. Denise got it. All right. Got lots and lots of winners. I'm sure I missed at least a couple of winners out there. But yeah, a bunch of you guys got this. That is super awesome. I got a sharp class this year, man. So what you guys were saying was that there's going to be a horizontal asymptote. Horizontal asymptote. And that horizontal asymptote would be the terminal velocity, wouldn't it? Call it V terminal. Terminal velocity. And if you drop something, say off the cliff edge, it's going to start out being pretty close to the no air drag situation, but then that air drag is going to pick up, and it will eventually reach some speed where it's not going to go any faster because the forces are balanced and it's going to be in equilibrium. It's going to go get all the way down. Now, what is that terminal velocity? Well, it depends on, say, these factors, especially cross-sectional area. Remember, if you jump out of a plane without a parachute versus with a parachute, how about this? Jump out of a plane without a parachute. just for funsies. And let's say this happens. Right? Okay. Then you go back and try this again. Well, maybe you should have done the opposite order, but anyway. So you decide, okay, with the parachute. Now, with the parachute, would this line be higher or lower? Yeah, definitely lower, right? Because a lower terminal velocity. Right. So what is this horizontal asymptote? Well, it depends, right? Do you have a parachute or not? Right, you guys get that? Right. Let's go back to free body diagrams. So back to, okay. I think I figured out what's going on here. I have to exit out of this PowerPoint. I have to flip back. I think I've solved this problem. For the video context, we're having a fun technical issues here. And we're back. Okay, so before terminal velocity, okay, looks like that. Okay. Next slide. What if there is air drag and it's gone all the way up to terminal velocity? At that point, the force is balanced, and now isn't that rock done speeding up? Right, so it's done speeding up and just go constant velocity all the way down. Okay, so it is in equilibrium. Right? From that free body diagram, can you look at that free body diagram? Let's say you know what those forces were. Can you know what the speed is? Not just from the forces. No. How about this? A boat moving through water at constant velocity. Boat moving through water, constant velocity. Does this boat have a weight? Yep. Does this boat have a what force is holding it up? Buoyant force. Kind of like normal force, but it's from a fluid, so buoyant force. There's probably some kind of applied force that's propelling it forward. Maybe the propeller pushing against the water. I'll call it applied force. Okay. And is that enough? Would that do it? No, because why? How do you know this is wrong? Constant velocity means all the forces must balance. There must be a drag force from the water. I guess that. Okay. And in fact, it must exactly balance out with the applied force. Okay. I bet if you turn up the engines on boat, went faster. I bet this applied force would get bigger. The propellers pushed against the water, but the drag force would respond and also become bigger, kind of like a terminal velocity kind of situation, right? Ooh, here's a good challenge. Can you guys figure out how to draw free forces so that it puts the object in equilibrium? Give you guys another shot on this. So see if you can do it. How can you make free forces that balance out? Equilibrium. Free forces in equilibrium. Check at least the front row here.
Why did two squares?
Everybody, at least in the front row, has got this.
What is this niche? Oh wait, I have an idea.
There's many solutions to this, so if you guys see if you guys come up with at least one. Maybe I'll walk around the room see if we can find at least one winner. There's got to be one winner in here somewhere.
Wait.
Close. You're close. That's okay. You know what, I haven't seen everybody's papers. I'm sure there's a winner somewhere out there. But here. How about this? Actually, you guys saw the answer yesterday. Here's one possibility. Right? Did you guys see the upside down version of this yesterday? You guys remember taking the spring scales? If you turn that picture upside down, there was like a 10 Newton going down, and there's like 10 Newtons up and to the left at 60 degrees and up and to the right 60 degrees. You guys remember that? Okay. So you could have done that 10, 10, and 10 at 120 degrees apart from each other. Or how about 10 Newtons up and then 5 and 5 down? That would do it too, wouldn't it? How about this? Parachuter before terminal velocity. So he's got his weight pulling down, and there's a drag force up that's less than his weight. You guys see that? Right. So that guy right there, maybe he just opened his parachute like half a second ago, and he's still speeding up. Right? But as he speeds up, isn't that drag force going to build up even more? Until, next slide, he has reached terminal velocity. So he's got to weight down, and then the drag force exactly opposes that. Right? And then he'll just go down at constant speed all the way down the ground. Okay. Here's the last one we're going to do today. This is going to be our stopping point. So I've got a rocket just screaming through space, constant velocity, 10,000 meters per second, deep space. So no planets nearby, no gravity tugs, anything like that. Okay. What does the three-body diagram look like for that? It's a three-body diagram. We're screaming through space, constant velocity. Oh, Sarah got it. Brian got it.
What?
You know what? I'm sure there's lots of winners out there, but got a piece spelled here. So, how do you guys said? That's the answer right there. That's it.
Oh.
Yeah. Isn't that? It's not the same thing as Voyager spacecraft. What's keeping the Voyager spacecraft going? Starts with an I. Inertia. Guys, if that rocket turns on its booster engines, what does it do? Starts with an A. Accelerates. What's this rocket not doing? Accelerating. So there you go. That's the answer. Oh, guys, last thing. Got a minute left. I know I've got like way too much information and not enough time, but I never got to this cup. So quick recap on the cup. Remember, see straw hole. Remember, I filled this up halfway with water. The water stayed in the cup. I filled it all the way up, and the entire cup drained. It didn't just go back to the previous level. The whole thing drained. Did anybody figure out how this works? Anybody figure this out? Bro, we will. We're gonna wait back for that. And finally, Songwriting Club starts today, tomorrow.